Okay, so in this problem, we are told a light beam strikes a 2 cm thick piece of plastic with a refractive index of 1.62 at a 45-degree angle. The plastic is on top of a 3 cm thick piece of glass for which n equals 1.47. What is the distance d in the figure? So I went ahead and redrew the figure that they give us. So essentially, we're going to have this light, right? This light beam is going to hit this glass. And then it's going to go like this, and then like this, right? So we know it's going to change a bit as a result of Snell's law. And then we're given some different things. So we're given the index of refraction for each of these two pieces of glass. So they're different, so they have different indexes of refraction. One is going to be 1.62. One is going to be 1.47. We're also given their thickness. So they're basically giving us this distance right here for each of them. So for this one, it's 2 centimeters, and for this one, it's 3 centimeters. So that's what we know. And what we're trying to figure out is this distance d from here to there. So let's talk about how we're going to do this first. So the first thing you need to recognize is that you can split this problem up into two main triangles. So if you imagine this as a triangle right here, so I'm just making this a right triangle, right, where this is a right angle. And then notice this is also a right triangle. And so what we're going to do in order to solve this problem is we're going to solve for this distance right here, d1, I'll call it, and then this distance of this triangle, which is d2. So you can call it d1 and d2. And what you should notice is if I can find this distance d1, and I can find this distance of this triangle here, d2, them added up will equal our d value. So what I need to find is those two distances, okay? And so in order to do that, what we're going to use is Snell's law. So I know these are triangles. If I can figure out the angle for each of these triangles, figure out an angle in it, well, that's going to allow me to actually solve for this distance because I'll have another component, right? So I know this length right here for each of the triangles. And if I know that in an angle, I can solve for this d1 value and this d2 value for each of them. So hopefully that makes sense. But let's go ahead and start solving. So the first thing I'm going to solve for is d1. As I said before, we need to find an angle in the triangle. And the angle I'm going to find is this one right here. And to do that, I'm going to use Snell's law, right? Because I know I have this light beam refracting. And I can find this angle, right? The angle of refraction by using Snell's law. So first, let's talk about Snell's law. So Snell's law tells us n1 sine of theta 1 is equal to n2 sine of theta 2. So n1 and n2 are your index of refraction. So n1 would be your initial, so we can call this 1, and this would be your 2. We're going to assume that it's coming from air. Okay, so the n from this would just be equal to 1. The reason that is the index of refraction for air is just 1. So n1 is 1. Theta 1 is your angle of incidence, which is the angle your light beam makes to the normal, or this line right here. Right? Normal means perpendicular to the surface it's going to be entering. So we know theta 1 is 45 degrees. N2 is your index of refraction, right, for your the thing you're going to be entering. So I know I called this N1, but keep in mind this is N2 in this scenario, right? So when we're plugging it in here, it's N2 since we're going from 1 to 2. So they just labeled it that way, but we can ignore that. So this is your N2 value. And then your theta 2 is your angle of refraction, which is the angle it leaves, right? So this angle right here, the beam it makes to the normal. So if we want this angle, we're solving for theta 2 in this equation. So it's really just a matter of solving for the values. So n1 is just 1 times the sine of 45, right? Because that's what theta 1 was, equals n2, which is 1.62, times the sine of theta 2. So you would divide both sides by 1.62. And then you're just going to take the arc sine of both sides to get rid of this sign. So your theta 2 value is the arc sine of this right here. So we have the sine of 45 divided by 1.62. So let's go ahead and see what this is. So sine of 45 dividing by 1.62, and then I'm going to take the arc sine of that value. So 25.88, we'll say. It's 25.879, so about 88. Keep in mind this is degrees. And so now we have theta 2. Keep in mind what theta 2 was. It was this angle right here. The angle of refraction. So, yeah, so this is 25.88. Let me label that. So 25.88 degrees. And keep in mind what we want to find now is D1. That was the whole reason we solved for this angle here. And the way we can do that is by using trig. So notice here, we can use tangent function. So we know the tangent of an angle. Right, actually, let me rewrite this. So the tangent of an angle, tangent is opposite over adjacent. So looking at our angle, the opposite side is D1, right? Opposite side of the triangle. And the adjacent side would be your 2 centimeters right here, this length. So the tangent of our angle is opposite D1 divided by your value right here, right? The adjacent, which is 2 centimeters. So your D1 value, you would just multiply both sides by 2. So it's just equal to 2 times the tangent of the angle, 25.88. And then let's go ahead and see what that is. So 2 times the tangent of 25.88. That is 0.97. Yeah, okay. 0.97. Keep in mind our units were centimeters here, so this is also centimeters. And yeah, so now we have our D1. We just need D2. So, yeah, so we know that. Let me draw this line a bit up like this, just so it's easier to understand. And yeah, so now what I need to do is figure out this angle right here, right? Just like we did on this one right here, we need to find this angle here. So I can just use tangent again and solve. So I need this angle, and how am I going to get that? So once again, we're going to use Snell's law, but keep in mind, I'm going to need, if you imagine this going up like this, I'm going to need this angle right here. Now, how can you find that angle? Well, there's a couple ways to do it, but I'll just show you. I know that this whole triangle, the angles add up to 180, okay? So this 25.88, this 90 degrees, plus this angle right here adds up to 180. If I know that information, I can solve for that angle, right? So that angle, we'll call it theta 3 for now. Doesn't really matter. Theta 3, right, is going to be equal to 180 minus 90 minus 25.88. I'm just taking the total and then minusing the other two angles, and that's going to give me what that angle is. So 180 minus 90 minus 25.88 equals 64.12 degrees. So if that angle is 64.12 degrees, I know this angle plus the angle we're looking for adds up to 90. So if I do 90 minus this angle, it'll give me that angle. And you'll see here, right, so if you do 90 minus this, you're just going to get the same value of our angle here. So these two angles are actually the exact same. Okay, so this angle is the same as this angle we just found. But I just wanted to show you how we found it. Right, you should just know by the laws that, or I forget what they're called, but basically the angle laws, essentially how it's lined up, you should know that they're going to be the same. But yeah, I just wanted to show you if you didn't know them. So based on the triangle, you can just figure out that it's 25.88. And so now that we know that, we can solve for this angle here using Snell's law once again. So once again, Snell's law is n1 sine of theta 1 equals n2 sine of theta 2. And yeah, so what is n1 in this case? Well, we're starting in this scenario. So n1 is 1.62. The angle of incidence, which we just found, is 25.88 equals n2. Well, we know it's going to be entering this one, so that's your n2 value. And then we're solving for this theta 2 value, right? Because theta 2 would be equal to this angle right here. So let's go ahead and solve. So you're going to divide both sides by 1.47 and take the arc sine. I don't need to show you guys how to do that again. So yeah, 1.62 multiplied by the sine of 25.88, and then divide by 1.47. So let's go ahead and see what this is. 1.67 times the sine of 25.88 divided by 1.47. And then I'm going to take the arc sine of both sides. So let me make sure I did this right. 1.62. Yeah, looks good. Okay, so your angle theta is 28.75 degrees. Cool. So this right here is 28.75 degrees. And then once again, to solve for D2, it's just going to be a matter of using trig. Since we know what this side of the triangle is, we can use tangent. So D2 is going to be equal to, you're just copying this formula again. So 3 times the tangent of 28.75. Right? Because the tangent equals the opposite, D2, over the adjacent. And then you just multiply both sides by 3. And that'll give you this. Right, so you'll get your D1. So let's see what this is. 3 times the tangent of 28.75. You get 1.6458. So I'm going to round to 1.65. Keep in mind, this is centimeters. And now we know D2. So with D2 and D1, we can add them up to get our D value. So plus 0.97. You're going to get 2.62 centimeters. Keep in mind, I did round there, though, so your answer might be a little different. You can just round to 2.6 if you'd like. I'll just leave it like this, though. But yeah, so round however you'd like, or however your teacher wants you to. But yeah, so your D value right there is 2.62 centimeters. So all we had to do was add up both of those. And yeah, so just a quick rundown. So all we did was use Snell's law to put these into triangles and solve for these D values so we can add them up. So the main trick is just recognizing that these are two separate triangles. And if I can split them up like this, I can find their individual components right here and then add them. And then it was just a matter of solving for the angles using Snell's law. So hopefully this video made sense. And yeah, hopefully you found it useful.